Hello, my name is Shelby Howerton, and this is my second lab of the motion of a falling object. In this presentation, I'll be discussing how I performed a real-life observation of a falling object and how I created two different computer models of the system, and then how I compared my real-life observation to the computer models. Lastly, I will discuss the principles involved in this experiment. The first goal in this lab was to implement Newton's second law with the non-constant force caused by the forces of gravity and drag. The drag force can be shown in one of our computer models and excluded from the other. We use the same position and velocity update formulas from last time to model the motion of the falling object in GlowScript. First, we analyzed the video in Tracker, and then we created a computer model in GlowScript. The system was the Sharpie, and the surroundings was the Earth. I dropped the Sharpie from about 1 meter high. This is a screenshot of the video in Tracker. I oriented the axis for the Sharpie moving in the negative y direction by placing the origin of the object's initial position. I rounded my axis to accommodate the calibration stick, which is set to the known height in the video. The video is about 11 frames, and the program gave me the position data of the object in the tables and the graphs. The graph has a slight curve in the slope indicating the non-constant net force and initial position and time range were obtained from the table, and we know the initial velocity of the object was 0 since it was dropped from rest. I analyzed my GlowScript programs, the mass position, initial velocity, and time range from Tracker. And here's my video now. Here's the code to represent the force of gravity and the position and velocity update formulas. This is the GlowScript program with only gravity affecting the net force. And here's my code. Here's the Sharpie marker moving downward, and then there's the position versus time graph, which has a curve, negative, and a negative slope, which is expected due to the acceleration of gravity. Then the velocity versus time graph and the position and time data the model produced to include drag force. I changed the net force to be the sum of the calculated force of gravity and the calculated drag force. I set drag equal to the coefficient of b, which is approximated through trial and error, and ran into the predicted final position best matched the observer of the position of the ball times the magnitude of the velocity squared times the positive j hat factor. Since the direction of drag is opposite to the direction of motion, I inputted all this information in my code, which is shown here. Running the code on the previous page, it included the arrows representing the drag. The position versus the time graph looks similar, and the velocity graph still exhibits a negative slope but is slightly more curved as it is trying to level out. These are the two graphs of velocity versus time. The code without drag is on the left, and the code with drag is on the right. The only slight differences are the graph without drag has a straight slope, negative slope, rather than the one with drag has this very small curve, and the line seems to start to level out. The model with drag is the best predictor of terminal velocity. It was just not very apparent as the time of the flight was not the full time needed to reach the terminal velocity. If the object was initially downwards, it would have a non-zero initial velocity. I manipulated my program with drag to have an initial velocity of 1 in the negative y direction and the velocity versus time graph it produces on the right. My model was not a great representation of terminal velocity, but one can see that the velocity with certainty near 4 meters per second, so I took that to be the terminal velocity. The graph of the model with initial velocity seems to start leveling out at around negative 4 meters per second. To determine the velocity sooner, we would have to make sure that the magnitude of the terminal velocity does not change. The time taken to each of it is just less. I created my comparison graph at the time of position data from Tracker in both computer and both computed models in GlowScript. This line graph was created by first inputting the position and time data from Tracker. The computer model without drag and the computer model with drag into a spreadsheet, and I plotted it into an Excel. The experimental data is shown in the gray dots with the blue dots in orange as well. Each curve is similar in shape, and the model of incorporated drag has a predicted final position closest. The observer final position kind of diverges from the observed position, and this could have been due to a blurred center of mass causing mistakes and placing the points in Tracker, or possibly an unaccounted outside force causing direction in the X movement. Some improvements I could have made in my lab is that I could have increased the height from which the object is dropped, Or I could have improved the positional data with a better camera or extend the position values for greater accuracy. And thirdly, I could have improved the calculation for drag force. My main objective was to use Newton's second law with the net force is non-zero due to gravity and drag the monitor to the motion of the falling object with the Sharpie.